Okay, good afternoon, students. Today we are going to see an design thinking based topic on wind farm behavior during the distribution sides, which is mainly integrated with network issue. So now coming to this topic, today first thing is empathy. What is the main empathy of this network, grid network issues? We know that globally wind capacity reaches about 906 gigawatts by the end of 2022. But growth in the wind energization and decarbonization, a main problem is grid integration challenges. We are facing grid integration challenges. So today, our focus, our empathy is to maintain the grid stability. So grid integrations is a main problem. That is the empathy of this part and grid stability, which is during voltage and frequency event. This is an empathy for our topic. Here, main, what is the define of problem definitions? We know that we have only 7.3 percentage of global electricity from wind energy. It is the variable nature sources, optimal. We have so many challenges. We are facing so many challenges. The main define of this problem is we have an old wind farm failed to meet grid requirement. That is, we know that old wind farm which failed to meet the grid requirement, which is typically what about tripping during distributions. These are main common issues for protections also. This behavior risk and it incorporated with the equipment damages and system blackouts. We have seen so many blackouts. Okay, these are the main definition of this define of this problem. Again, coming to the define of this problem, we have two types of implementation, define implementation. One is type 3 DFIG, next one is type 4 full converters. We have two types of motors which is already used. This which reaches which gives the networks issues. This is also define of the problem. So we have fault right through techniques, and moreover we have so many techniques of wind farm mechanism. So anyone can say what are the techniques we have seen in wind farm mechanisms? Anyone from this?
Responsive mechanisms are older designs, modern designs, and the older designs include type 1 to SCIG, often tripped for protection, and the modern design includes a typical 3-4 equipped with FRT capability, and it also includes codes and reactive support. The grid codes are mandate staying connected during faults, and for reactive support, we are using injected reactive power to stabilize voltage.
Challenges. Can anyone say what are the challenges on during the integration process, grid integration process?
Key network integration challenges. It's like integrating wind power poses several challenges like reduced system inertia impacts frequency stability and dynamic voltage and control crucial during faults. Harmonic power consumptions affect harmonic power converters affect quality. There are a few types. The first one is inertia reduction. It has a less rotating mass, impacts frequency. And second one is voltage stability. It has high reactive power demand during faults. And the third one is harmonic distortion. Converter switching affects power quality.
So now we'll be having small activity on in Kahoot. So let's start the game. So game starts. So 43 percentage answer. So now here comes the result of this game. First place goes to second Sudiksha. Third one. Who is the first place? Just stand up. Who's the first one? Okay, good. Second, second, who's second place? Third place, who's that Palani brothers? You four. Sit down. The mitigating strategies and techniques. This comes under the ideate part in design thinking framework. So, can anyone say any technologies and strategies we are going to use for address this issue of grid integrations? Can anyone from this? Others?
So when we see about the mitigation strategies and techniques, advanced grid codes are crucial for stability. Fax devices provide dynamic voltage requirements. Energy storage system offer fast frequency response. Synchronous concentrators provides inertia. Advanced control algorithm optimize turbine response. Advanced grid codes. In this, strict FRT curves, enhanced reactive power support. For the next fact devices, in this, STATCOM SVCs for dynamic voltage regulation. In energy storage, BESS for fast frequency response, synthetic inertia.
Example shows the path of reliable integrations. So here comes. First one is South Asian blackouts, wherever the wind form is stripped and systematic is collapsed. Okay. The next one is what lesson we have learned from this, and that is a need for robust fall reduction techniques and dynamic supports. This is the lesson learned from the blackouts. And the next one is grid programming. So highly non-synchronization and penetration. This is then a programming. We should be more strong in programming networking. So that is the main thing we are discussing here. And finally is German's grid. So coming to the conclusion, futurely we have to focus on AI driven management system. This is the main conclusions. We have summarizing this topic. Can anyone from this audience can summarize this topic?
Let's summarize wind from behavior during the grid disturbance and grid integrations, context and imperatives, wind turbines types and technology, understanding the grid distributions, key network integration challenge, real world and impacting solution, and the future outlook.
Okay.